Let's talk about calculating average reaction rates. For any general reaction, such as the one shown here, where the lowercase a, b, c, and d refer to the coefficients, these are the numbers in front, and the capital A, B, C, and D refer to the molecules you actually have, you can write an expression for the average reaction rate, that's that rate right there, in terms of any one of the reactants or products. So reactants always get a negative in front because they decrease over time. Products increase over time, so they get a positive. And all you do is put 1 over each coefficient, and then you have the rate of each reactant and product. That's this delta expression right here. So delta A over delta T, that's the rate of change of A. Delta B over delta T, that's the rate of change of B. So what we're doing is we're relating the rate at which any one reactant or product changes to this overall rate of the reaction. How often does this overall cycle take place where A and B are converted into C and D? So the language here is really important. Are you looking at the rate of the overall reaction? That's this rate right here. Or are you trying to look at the rate of an individual molecule? That would be these delta A, B, C, or D over delta T that we see here. So we're going to have to pay close attention to that when we work these problems. So this expression is known as the average reaction rate, or it's also sometimes called the differential rate. And it's important to note that we have to use this expression if we're trying to calculate the rate of a reaction. We cannot predict it just by looking at the chemical equation here. The coefficients tell us something, but they don't tell us how fast the reaction overall is. So we always have to take some data measured in the lab, and then we can determine the overall reaction rate. So let's look at an example of a problem. Example, calculating average rates. So the following reaction takes place in a 250 milliliter flask. We have this reaction here. First question we can do just by looking at the chemical reaction. Express the rate of the reaction with respect to each of the reactants and products. Okay, so we're always going to do rate equals. I'm going to abbreviate here, R equals. So we just look at each reactant. Reactants get a negative, and we have a 2 here, so I'm going to do 1 over 2, right? I make that into a fraction. And then I'm going to do delta into O3 over delta T. So that's my only reactant, so from now on it's going to be positive. For my first product, I have positive 1 over 2, and then it's delta into, oops, it's a little small, it's all right, over delta T. And then my second product, still positive, but now I have a 3 in front, so 1 over 3 delta O2 over delta T. So this is really expressing all of my possibilities. I could figure out the overall reaction rate by measuring either into O3 or into or O2. I could figure out the rate from looking at any one of these. Now the next question actually wants me to do the calculation. What is the average rate? So what I need to do is look at this table it gives me and see what molecule it gives me information about. And the answer is into O3. So I don't have to use this whole equation here. I only need to use the piece, what do I want, which is my rate right here, and what did it give me, which is the into O3. So I'm just going to pull that part down. Rate equals negative 1/2 delta into O3 over delta T. And that's the only part of it I'm going to use. I don't need this part right now. It didn't say anything about nitrogen, anything about oxygen, so I just don't need to use that part of the equation. So now what I need to do, it wants the rate between 10 and 20 seconds, so I'm just going to pay attention to this part, and I'm going to plug in my information. So I have my negative 1/2 in front. Between 10 and 20 seconds, the concentration change is given here, and I always do final minus initial, so there's decimal there, 1.175 molar minus 1.236 molar on top. And on bottom, I do the time, final minus initial, 20 seconds minus 10 seconds. And now I just plug that whole thing into my calculator, and I find that my rate is 0.00305, and I keep units, molar per second. I always want to include my units on that. So the average rate at which 2 of these into O3 molecules are converted into 2 nitrogens and 3 oxygens is 0.00305 molar per second. That's the rate of the overall reaction. Now sometimes it doesn't want the rate of the overall reaction. So again, pay very close attention to language. So let's look at a different question it could ask me. So here I've just rewritten this expression. It's a lot more legible now. But now my question asks for the rate of formation of oxygen. Doesn't want the overall rate of the reaction now. So I'm going to look back at my equation. I'm going to do the same thing we did before. It wants the rate of formation of O2. So what it's really asking for is this delta O2 over delta T. That's the rate of O2. So I'm going to have to use this part of the equation. So I'm just going to go ahead and write that part down here because that's what I want. So I know I want that in my answer. And again, I have to look at what it's given me. It's given me information about N2O3. So that's the other part of this I'm going to have to use. Equal to negative 1/2 delta N2O3 over delta T. It doesn't care about the average rate anymore, so I can cross that guy out. And it's still not saying anything about nitrogen, so I can cross that guy out. I'm only going to pick out the two pieces that I actually want. One is the piece that I want. That's, in this case, the rate of O2. And one is what they gave information about. That's the N2O3. And I'm just going to ignore everything else. So what I'm really solving for is in this parenthesis here, the change in oxygen over time. So some people like to put a big X there because they like to solve for X. It makes them feel better. Whatever you want to do. But since this is what I'm solving for, the very first thing I'm going to do is take this whole thing and multiply by 3 so I can cancel out this 1/3 here. So I get delta O2 over delta T is equal to 3 times negative 1/2 delta N2O3 over delta T. So I want to solve for the change in oxygen over time, so now I just need to plug in some numbers. So I have 3 times negative 1/2. Now I go back, it wants between 20 and 30 seconds. So that's what I'm going to pay attention to. On the top, I'll put the change in N2O3, so 1.118 molar minus 1.175 molar. On the bottom, final minus initial, 30 seconds minus 20 seconds. So now I just need to plug this whole thing into my calculator. Subtract the top, subtract the bottom, and multiply by negative 1/2 and 3. And I find that overall, the change or the rate of formation of oxygen is 0.00855 molar per second. So just pay attention. Is it asking you for the rate of the overall reaction like the last problem? Or does it want the rate of a specific reactant or product like it did in this question? And then you just go back to your overall equation, pick out the piece you want and the piece it gave you information about, and you go from there.